In this lecture, we're going to learn about 3D principal stresses and the absolute maximum shearing stress and 3D Mohr Circle. First, we're going to talk about the 3D principal stress state in tau maximum absolute. So, if you remember from our previous lecture, we talked about what's called a 2D Mohr Circle, and we started with a state of plane stress. And let's just review what we know about stress states and Mohr Circle so far. So, in a state of plane stress, we have our stress components in the x and the y direction, sigma x, sigma y, and tau xy. One of the things that we learned what to do was to use our Mohr circle to find our principal stresses. And this is what we call a plane stress state. All the non-zero stresses lie in one plane. And if we use Mohr circle, we can find our principal angle. I'm going to draw it off to the side, theta p, and one of these stress components off in this new direction is sigma p1, the other is sigma p2. I'm just going to assume that the one this direction is sigma p1 and this other one is sigma p2. So those are our two principal stresses. And no matter how our stress state started out looking like, if we were looking at our Mohr circle, sigma p1 and sigma p2 would be these spots located on that Mohr circle. So sigma p1, 0 and sigma p2, 0. One of the things we talked about in that lecture was what's called the maximum in-plane shearing stress. So as I rotate my little block around the z-axis in the xy plane, I can change the values of sigmas and taus until either the sigmas are a maximum or the taus are a maximum. We know when we talked about Mohr circle that the maximum shearing stress diameter of Mohr circle was represented by the vertical diameter right here, and this would be the point sigma average comma plus r, the radius of the circle. This would be the point sigma average comma minus r. And so tau maximum, what I'm going to call in plane, meaning in the xy plane, as I have it defined here, would be the radius of our, what I'm going to call as our two-dimensional circle for the two-dimensional stress state. Now we can think of that in terms of the radius, or if we want, we can think of that as the diameter of that circle divided by 2. And the diameter of that circle we can find in terms of the principal stresses. If I take sigma p1 and subtract sigma p2 divided by 2, just kind of keep things from going negative on the dimension there, let's make that an absolute value, then I can find the radius of my circle, maximum in-plane shearing stress in terms of my radius of my circle or the principal stresses. Now in general, there are always 3 principal stresses, not just 2. Even when my stress state looks like a state of plane stress, it turns out I have 3 principal stresses, and just one of them is equal to 0. Let me draw a cube of material. And a more general stress state would have not only a sigma x, a sigma y, and a tau xy, but we could have a sigma z, a tau xz, and a tau yz on that cube of material. There's also stresses on the back faces that I'm not drawing in. So this is a general state of stress. Now, the way that we've defined principal stresses is we say they're the directions in which the shearing stresses vanish. So if you can imagine taking that cube and rotating it in space, think of it like maybe a die from a game. You take that cube and you reorient it in space, there will be 3 directions in which the shearing stresses on all those faces disappear. And they'll be perpendicular to each other. Sometimes I have a hard time drawing this, but I'm going to give it a shot. Suppose my cube is oriented this way, and all those shearing stresses vanish, and all I'm left with are normal stresses on those faces. This would be sigma P1, sigma P2, and sigma P3, or however you want to order them. Some people order them maximum to minimum. Some people do something different. But the idea is I can tell that those are principal stresses because the shearing stresses on those faces have gone away. They're gone to zero. Okay, so just to say that again, in general, we have three principal stresses, and we can reorient that cube and find them. We can identify that these are principal stresses because the shearing stresses on those faces at this new orientation have gone away. Those have vanished. Now, just like we saw that there was a principal stress that was the difference between sigma P1 and sigma P2 on our 2D Mohr circle, and that lies 45 degrees in between the sigma P1 and sigma P2 axis, we also have maximum shearing stresses that lie in between the sigma P2 and the sigma P3 direction, and the sigma P1 and the sigma P3 direction. So there are three local maximum shearing stresses. I'm going to call this one tau max 1, 2. It would be sigma P1 minus sigma P2 divided by 2. Tau max 2, 3 would be sigma P2 minus sigma P3 divided by 2. And tau max 1, 3 should be sigma P1 minus sigma P3 divided by 2. Each of these occur 45 degrees in between the respective principal axes. Now, the largest of these three is what we're going to call the absolute maximum shearing stress. So tau maximum absolute, I'm going to abbreviate this ABS underneath there, but absolute is equal to the maximum of these three combinations, these three possibilities: tau max 1, 2, tau max 2, 3, and tau max 1, 3. So now the trick is, if we are able to find three principal stresses, then we can find our absolute maximum shearing stress. It's important for us to know what our absolute maximum shearing stress is because some materials are very sensitive to shearing stress and they may fail. They may yield due to high shearing stresses. So we want to know not only what that value is, but where it occurs, 45 degrees in between which set of principal axes. Okay, so now let's talk about how we need to, what we need to do to figure out what our three principal stresses are. Now there's kind of a sophisticated way to figure out what the three principal stresses are if you have all these different stress components. And we won't do this in my class, and you may not be able to do this yet. You may not have the background for it yet, depending on what classes you've had. But just to give you an idea of what we need to do, if we were to arrange the stress components in a matrix like this, it's symmetric, where we have the shearing stresses on the off-diagonal terms and the normal stresses on the diagonal terms. and solve what is called an eigenvalue problem, we will find the maximum stresses. Now, you may not have heard of the term eigenvalue problem unless you've had a class in something called linear algebra. A lot of engineering students take linear algebra, but maybe not before they've taken mechanics of materials. So that's a little bit sophisticated for us right now. I teach other classes where we go into great detail about solving eigenvalue problems. But we're not going to do that in here. What we are going to do, though, is we're going to take a look at a special state of stress called generalized plane stress. And let me just make a note about that. State of generalized plane stress, if I were to draw it on my cube, has the same components as plane stress, where I've got a sigma y and a sigma x and a tau xy. But in addition to that, I have a stress component, sigma z. It's coming out in the z direction. Okay, I probably ought to put a note here. Not for my class. Okay, so generalized plane stress, if we look at that sigma z, on this face right here, let me shade it in a different color. On this face, there is no shearing stress. Because there's no shearing stress, that automatically means that that stress, sigma z, is a principal stress. And I am going to call that principal stress sigma P3. Now, like I said, some people, some books order these to be greatest to smallest, and I don't necessarily know if that's the smallest one yet, but I'm just going to label that sigma P3. We'll sort all that out later. All right, so now if I know that that is my third principal stress, all I have to do is use a 2D Mohr circle in the XY plane to find my two principal stresses, sigma P1 and sigma P2, and then my third principal stress would be sigma 3, and then I've got it made. I can compute my absolute maximum shearing stress. Okay, now there's a graphical way to keep track of all this, and that's where this thing called 3D Mohr Circle comes in. And of course, a circle isn't 3D, but it's the stress state that's 3D that we're talking about. And so I'll show you how to set up this thing called 3D Mohr Circle next. All right, so for 3D Mohr Circle, we have our state of generalized plane stress. Instead of drawing that three-dimensional cube, I'm drawing it flat again, but sigma z is coming out of the page at us. We're going to be pushing into the page. The point is tau xz and tau yz are equal to 0. Now, sigma z could be 0 too, or it could not be 0. It just could be a number, and that's an important thing to note. Is really everybody should always be doing a 3D Mohr circle, and we'll show why that is very soon. So the first step in constructing what's known as a 3D Mohr circle is to simply make a 2D Mohr circle. Using the in-plane stress components, sigma x, sigma y, and tau xy. All right, so remember how to do that. Just as a quick review, we plot 3 points. We plot what we call our x point, which is sigma x, comma tau xy, our y point, which is sigma y, comma minus tau xy, in the center of our circle, which we locate at sigma average comma 0, where sigma average is equal to the in-plane stress component sigma x plus sigma y over 2. Let me draw this down here a little bit. I'll try to make a circle in straight lines, but as far as my circles go, that's pretty good. So here I have sigma and tau. Remember, my convention is positive tau is downward. Some books use these arrows that go like this to indicate rotation directions on the positive x and y faces. Same difference. Here's the center of my circle, and let's just say that my x and my y points were such that it landed in this position and in this position. We know that this point and this point are sigma p1 comma 0 and sigma p2 comma 0. Well, I'm going to call the first and second principal stresses. And we get that by the usual way. We find the radius of the circle, and then we take the average plus and minus the radius to get to those values. Now, here's what we do to make a 3D Mohr circle. And again, this only works for a state of plane stress or generalized plane stress. Is we plot an additional point, which is going to be sigma p3 comma 0, which if tau xz and tau yz are 0, it's going to be sigma z comma 0. Now this third point could fall anywhere of 3 spots. Suppose sigma z was bigger than sigma p1. It would plot over here somewhere. Suppose sigma p3 was less than sigma p2. It would plot over here somewhere. Suppose it was in between, then it would plot in between sigma p1 and sigma p2. Wherever it lands, that's where you plot it. It could even be the same value as sigma p1 or sigma p2. But we don't want to make it look too confusing, so I'm going to say it lands over here for my drawing. And this is going to be my point, sigma p3 comma 0, which is the same as sigma z comma 0. Now here's what you do, and I'm going to switch to a different color. You draw 2 additional circles that connect sigma p3 with your other 2 principal stresses that you've already found. So I have a circle that's a little bit smaller between the 3 and the 2 principal stress, and I have another circle that's a big one that goes between the 3 and the 1 principal stress. All right, so let's make that step. We draw these 2 additional circles, sigma p3 to sigma p2, sigma p3 to sigma p1. So that is a 3D Mohr circle. Now, from this circle, we can also find out whether or not what their value is of our absolute maximum shearing stress. Remember on the previous page, we wrote the absolute maximum shearing stress as the difference between the 2 principal stresses divided by 2, each different pair. Well, I can look at this, and the biggest radius, or the biggest diameter over 2 for all of these 3 circles that I have drawn here is my absolute maximum shearing stress. So it's your biggest radius, so it's your biggest diameter divided by 2. In this case that I've drawn here, it would be sigma p3 minus sigma p2 divided by 2 would be my absolute maximum shearing stress. The direction that that occurs in will be 45 degrees in between the sigma p1 axis and the sigma p3 axis. Now the sigma p3 axis is the z-axis in our picture. In this case, what we would call this is 45 degrees out of plane maximum shearing stress. I'll write this on the next page, but if your absolute maximum shearing stress is associated with the 2D Mohr circle, if that's your biggest circle, then we have what's called an in-plane maximum shearing stress. If your absolute maximum shearing stress is associated with one of the extra circles, then we have what's known as a 45-degree out of plane maximum shearing stress. Let me write that down, and I'll show you the cases for Mohr Circle. Okay, just to say that again, if your biggest circle is not the 2D circle, then we say tau maximum absolute is 45 degrees out of plane. Some people put dashes between those words. And if your biggest circle is the 2D circle, then we say that the absolute maximum shearing stress is in the plane, in the XY plane. So let's draw a couple cases here. Here's our 2D circle. We found our sigma P1 and sigma P2. And maybe I'll draw it this way. Our sigma P3, sigma Z is over here. We draw these two additional circles. Notice how the biggest circle is not the 2D circle. That means tau maximum absolute is 45 degrees out of plane. Some people abbreviate that as OOP. I'll spell it out of plane. In a separate case, suppose we do a Mohr circle calculation. We got our 2D circle, and here's sigma P1 and sigma P2. And our sigma Z happened to be in between those two values. There was sigma P3 equal to sigma Z at that spot. Then we draw these two smaller circles that they go inside my 2D circle. Then we would say tau max absolute is in plane. And this case is when R2D is our maximum circle. All right. So for some of your homework problems in this section, you're probably going to have to construct a 3D Mohr circle. You're going to have to find your absolute maximum shearing stress, and we can do that just based on the size of these circles. It is not uncommon to have an absolute maximum shearing stress that is 45 degrees out of plane. You should always check for it. There's nothing worse than doing all these calculations and missing where your material is going to fail, or even if it fails, and that's quite possible if you don't consider that the absolute maximum shearing stress could be 45 degrees out of plane. Very important. A little bit later on, we're going to talk about a subject called pressure vessels, and in pressure vessels, it's very common that the absolute maximum shearing stress is 45 degrees out of plane. Just kind of depends on the relative values of your sigma x and your sigma y and your sigma z. All right, so that's it for 3D Mohr Circle. What I'm probably going to do is I'm going to come back and fill in with some examples with numbers in them in separate videos.